following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
Finite difference methods for initial value problems that we're coming to the end of, and the solving large systems that we're coming to the beginning of, was to talk today about matrices, because that language is just useful for everything. And so about the homeworks, Mr. Cho put in a long weekend grading the homeworks that were turned in Friday and preparing code and output to go up on the web page, probably late tonight or tomorrow. So have a look to see, and I hope that those codes will be useful for the future too. Right. Okay. So we'll maybe say more about the outputs and about the projects, which, by the way, could grow out of that homework or could go in a totally different direction. I'm thinking that the right time to say projects due would be after spring break. So pretty much nearly immediately after the spring break would be, and we'll talk about more, but just so you have an idea of what timetable I had in mind. Okay, so matrices then. And in particular, finite difference matrices. So that's the second difference matrix, K, and I'll frequently use that letter K as I did in 18085 for that very, very important and useful matrix. So what are its properties? It's tridiagonal. That's a very important property, which we'll see, because that means that computations solving linear systems was very fast with a tridiagonal matrix. It's symmetric. All its eigenvalues are positive, so I would say it's symmetric, positive, definite. And those eigenvalues and eigenvectors, so the eigenvectors for this matrix turn out to be discrete, not quite discrete exponentials, discrete signs, discrete sign functions. If I change the boundary conditions, I can get discrete cosines as the eigenvectors, or I could get discrete exponentials as the eigenvectors by making it periodic. Maybe I'll mention how to make it periodic and then I'll erase it again. To make it periodic means that this second difference centered at point 1 should look ahead to point 2 and look behind to point 0, but that'll be the same as point n. So I would put a -1 in that corner, and this one similarly, it looks ahead, and which really brings it around again, since we're sort of on a circle, brings us around again here. Okay, so that matrix now with -1s added in the corner, I would call C, a circular. So I'll leave the letter K there, but the right letter is C, while these -1s are here to make it periodic. And by the way, so they mess up the tridiagonal. It's no longer tridiagonal, although it's certainly it's very sparse. And mentioning sparse reminds me, if you're coding large matrices that are sparse, you should let MATLAB know that they're sparse. So MATLAB has a whole, it carries out operations. If you tell it it's a sparse matrix, then it only operates where the non-zeros are located. And it doesn't waste its time looking at these zeros through all the matrix steps. So, using sparse MATLAB is an important thing to know about. And it's just typically an S or an SP will appear in MATLAB commands. For example, I'll just maybe fill it in here. what's the sparse identity matrix? The normal identity matrix would be I of n, and the sparse identity matrix is SP, SPI of n. Okay. And similarly, we would create K. Well, we could use 2 times SPI of n as the diagonal of K, and the upper and lower diagonals, and we could tell it these 2 entries. Another thing to say, well, what I said I wasn't going to do, I'll do, because I hate to see a K up there while it's not right. And two more points about this matrix. It's singular now. The determinant is 0. Now, I'm never going to take the determinant of a giant matrix. That's a bad thing to do. Much better to recognize that there's a vector x, let's say, and it's the vector of all ones. It's the vector of n ones. If you imagine multiplying this matrix by the vector of n ones, what do you get?
0.
You get all zeros. So that vector of all ones is in the null space, I would say, of the matrix. Null space is just the vectors that get wiped out by the matrix. Cx is all zeros. So that vector, this matrix has some non-zero vectors in its null space, and I know right away then its determinant is 0. So the determinant of that is 0, and now that would tell me something about the eigenvalues of the matrix. Well, it tells me about one eigenvalue. It's 0. A matrix like C that has Cx equals 0, well, I could also say that that's Cx equals 0x. That would actually be better, so that both sides are vectors. And so I'm realizing that that vector x in the null space is an eigenvector, and the corresponding eigenvalue is 0. And so that's, otherwise the eigenvalues will all still be positive. So this would be a positive semi-definite. So I would call that matrix positive semi-definite. The semi telling me that it isn't quite definite, that it gets down and has 0. So the matrix is singular, but still, it's good to know where all the other n-1 eigenvalues are. They're all positive. Okay. Okay. About the bandwidth. Let me go back to K now. Because the bandwidth, strictly speaking, the bandwidth of C is very large. The bandwidth is, if I'm looking for only one number, that number tells me how many diagonals I have to grow until I reach the last non-zero. So the bandwidth here is large. And in general, the operation count, the amount of work to do, is going to grow with the bandwidth. Well, of course, that having full bandwidth isn't quite the full story for this matrix because it's so sparse. I've got like hundreds of zero diagonals in between and just this one. Anyway, this is a matrix with a large bandwidth, but a little deceptive. Now, here's a matrix with a, back to K again, I call the bandwidth just 1 here. Really, maybe half bandwidth would be a better word. The bandwidth is the number of diagonals above or below. Take the maximum of the count above and the count below, and in this case, both counts are 1. 1 diagonal above, 1 diagonal below, so really half bandwidth, I would say, is 1. Okay. Just some convention is needed there. The crucial point is that the bandwidth measures the amount of work to do when you do elimination, as MATLAB will do, of course. One other thing about MATLAB. So I'm often referring to MATLAB, and I'm thinking of its backslash command, the backslash, which solves AX equal B by just A backslash B. So if it doesn't know these matrices are sparse, it will go through all the steps, not taking advantage of the fact that we've got all these zeros here. If it does know that they're sparse, then it's tremendously fast. Let me come back to that point. Well, maybe actually backslash is smart enough to look to see whether the matrix, whether sparseness is available. So I shouldn't have said. I think maybe there's a lot engineered into backslash. Actually, backslash also engineered in there is this least squares solution. If you give it a rectangular problem and say too many equations so that you can't expect to have an exact solution B, backslash will pick the least squares solution, and much more. That's probably the most used operation. Okay. So I said something about the eigenvalues, and everybody sees that if I multiply this matrix by the values of U at successive mesh points, I'll get the second difference that corresponds to UXX. Now this matrix, so that tells me I'm taking a finite difference. That plus tells me I'm going in the forward direction. So that's 1 at the mesh value to the right minus 1 of the mesh value at the center point. And of course, this has to be divided by delta x, and that by delta x squared. So these are matrices along with the backward difference and the center difference, out of which you build the basic finite difference equations, as you've done. I want to make a comment here, though, about now on this topic of eigenvalues. Eigenvalues for K really tell you the truth about the matrix K. The eigenvalues of that matrix K start just a little above 0, and they go to a little before 4. So the eigenvalues for K, so I put that here, the eigenvalues of K are between 0 and 4. They come very close to 4 and quite close to 0, depending on the size of the matrix. Of course, let me just do, if I took the 1 by 1 case, its eigenvalue is 2. If I took the 2 by 2 case, its eigenvalues are 1 and 3. Notice nice properties there. The eigenvalues 1 and 3 are positive, as we said. This matrix K has positive eigenvalues, whatever size. And what's more, the 1 and 3 kind of interlace the 2. So what I'm saying is that the eigenvalue for that is in between the eigenvalue for the 2 by 2. And the 2 eigenvalues, 1 and 3, are in between the 3 eigenvalues that I would get for the 3 by 3 case. Maybe I just write those down. They're useful numbers. So K2 has lambda equal 1 and 3. The 3 by 3 one I think the eigenvalues are 2 minus root 2, which is smaller than 1, 2, which is in between, and 2 plus root 2, which is larger than 3. And of course, they're all between 0 and 4. Just a comment. How do I know they're between 0 and 4? Well, there's a somewhat handy little rule for getting the location of eigenvalues. That's just worth knowing as a sort of general principle, but of course, it can't tell you exactly where they are. Well, first of all, the fact that the matrix is symmetric tells us what about the eigenvalues? So we learn a very, very important fact about the eigenvalues from just looking at the matrix and observing that it's symmetric. That tells us the eigenvalues are real. They're real numbers. And actually it tells us something equally important about the eigenvectors. The eigenvectors of the matrix are orthogonal. A symmetric matrix has real eigenvalues, orthogonal eigenvectors. That's a little bit of linear algebra to know. Now, why between 0 and 4, though? Well, there's this, what's his name, Gershgorin? Gershgorin pointed out, and it's a two-line proof, that every eigenvalue is in one or more of his circles. So where are the Gershgorin circles? Well, a typical Gershgorin circle is centered at the number here 2 that's on the diagonal, and its radius is the sum off the diagonal, but you take absolute values. So Gershgorin wasn't like doing any of the fine points that really locate the eigenvalues. So in this matrix, all the centers are at 2, the diagonals, and the radii are 2, also 2, because that and that in absolute value make 2. This first row makes a 1, and actually that's what, that by a little careful argument, is what gets the eigenvalues not actually touching 0 or touching 4. Yeah, it takes a little patience. All you could say from here, all Gershgorin could say would be the eigenvalues are in a circle, centered at 2, its radius is 2, so they're between 0 and 4. And then it's that first and last row, or either the first or the last row would do to say that they're strictly positive. And of course, the true second difference, I should divide k by delta x squared. So the eigenvalues will be divided by delta x squared, divided by a small number, so they will really be much larger. But the ratio of the biggest to the smallest isn't affected by the delta x squared, and that's a key number. Let me put that maybe on the next board for k. Okay. So lambda max is about 4. Lambda min, the smallest eigenvalue, is close to 0. And how close? It's of the order of some constant over n squared. And now I use the word condition number. And so let me write that down. Condition number, say C of k for condition number, is the ratio, lambda max over lambda min. Of course, I'm using here the fact that k is a symmetric matrix. Symmetric matrices are so beautiful that their eigenvalues give you a reliable story here. So 4 divided by this, the main point is that it's it's of order 1 over n. When I divide by lambda min, that puts the n squared up in the numerator. And it's O of n squared, growing like n squared. And that condition number somehow it measures how close the matrix is to being singular, because it involves this lambda min, which is the smallest eigenvalue and would be 0 if it were singular. And it's scaled by lambda max, so that if I multiply the matrix by 100, what happens to the condition number? No change. No change, because I'm doing lambda max over lambda min. Both lambda max and lambda min would be multiplied by 100, but the ratio wouldn't be different. So this is a useful measure. And O of n squared, well, that's a big number if n is large. A big number if n is large. And that condition number, where does it come? In elimination. In elimination, the Roundoff error, well, roughly, the rule of thumb is that you would, if the condition number is 10 to the 8th, you might lose 8 significant bits in the backslash. You could. So this condition number measures how sensitive your matrix is to roundoff. Okay. So that's a few thoughts about matrices and that matrix K in particular. Now, what about the other matrix, the first difference? Well, the point I want to make about that matrix is, what about its eigenvalues? What are the eigenvalues of that upper triangular matrix? They are, if you remember linear algebra, but I can just tell you quickly the main point. For a triangular matrix, the eigenvalues are sitting on the diagonal. So this matrix has the eigenvalue -1 repeated n times. And that true fact is totally misleading. Totally misleading. The eigenvalues for this triangular matrix don't even notice what I've got above the diagonal. And somehow they can't give a reasonable picture of what the matrix is actually doing. So maybe that's my warning here, that for a matrix which is absolutely not symmetric, right? I mean, not at all symmetric. For the center difference, which is, well, okay, what's the center difference? I was going to say symmetric, but it's the opposite. Center difference would be, let's put delta centered down here. Center difference would be, I'd have a 1. Zeros would go on the point that, for the central value. 1 would multiply the forward value, and -1 would multiply that, and then I'd have a half, and I'd probably have a delta x. But the main point is, my matrix would look something like this: -1s and 1s on 2 diagonals. Now, we could find the eigenvalues of that matrix. Do you know anything about the eigenvalues? This is like a chance for me just to speak for a few minutes about useful facts that you can tell about a matrix just by looking at it. So what do I see when I look at that matrix? Is it symmetric? It's the opposite of symmetric, because the symmetric matrix up there, if I transpose it, it doesn't change. If I transpose this one, I'll get some kind of a backward difference. If I transpose this one, then the ones and the minus ones will reverse. I'll get the negative. So the rule for this center difference is, so how am I going to call center difference? Del centered for the moment. The transpose of that is minus itself. So what does that tell me? First, that matrix is, well, it's the opposite of symmetric, but it's actually okay. What I mean by okay is its eigenvectors, we're back to orthogonal eigenvectors. I didn't say anything about the eigenvectors of del plus, but actually that was the biggest problem. This matrix del plus has one eigenvalue repeated n times, and it has only one eigenvector. It doesn't even have a full set of eigenvectors, much less orthogonal ones. So that matrix is like, you don't want to trust the eigenvalue picture that you get from a matrix like that. Here, this anti-symmetric matrix can be trusted. Its eigenvalue picture is reliable. It does tell you what's going on. The eigenvectors are orthogonal. They're complex, actually. Actually, they'll look a lot like our e to the I kx's. So we don't like panic when we see a complex eigenvector. And the eigenvalues are, do you know what the eigenvalues look like for an anti-symmetric matrix? They're pure imaginary. Just the way that when we took second differences, maybe I'll just put here the center difference, the centered first difference. When we applied it to, I want to apply to e to the I kx to find what factor comes out. So I get e to the I k plus 1 delta x from the plus side. This is the matrix I'm doing with 1 and minus 1. So the minus 1 will give me minus e to the I k minus 1 delta x. And of course, I factor out of that the e to the I kx's. So I'm left with e to the thing that factors out is e to the I delta x minus e to the minus I delta x. And what's that? So that multiplies the e to the I kx, the eigenvector. And this is like the eigenvalue. And what do I see about that quantity? Of course, it's 2I sine delta x. Pure imaginary. And I should have divided by the 2, which would take away that 2. So it's pure imaginary. In reality and in this Fourier analysis, both are giving this understanding of what I is. So that when we did this sort of operation, von Neumann's rule of following the exponentials, we got something reasonable. When we do it with this one, it's von Neumann that's reliable and the eigenvalues that are not reliable. So the eigenvalues of this being all minus ones is nonsense. Doesn't tell us what the forward difference operator is really doing. But von Neumann tells us what is truly going on. Of course, that would be the same thing in which this minus 1 wouldn't appear and the 2 wouldn't appear. So what would we get out of von Neumann? So this is for delta plus. I would factor out an e to the I delta x minus 1. That's what would multiply e to the I kx. Oh, e to the I, sorry, there's like, yes, no, that's right. That would multiply e to the I k delta x. Sorry, I should have had delta x there, but I wasn't paying attention to that. Here I was paying attention to this, and it was pure imaginary. Here I'm paying attention, here von Neumann at least is paying attention to this, and what's he seeing? Not pure imaginary, or purely real, off in the complex plane, and that's really what the right growth factor or the right number to associate with frequency k for this forward difference. Okay, so I guess I'm saying that von Neumann did the right thing to come up with these pictures for the growth factors. Eigenvalues confirm that and really pin it down when they're reliable. And eigenvectors and eigenvalues are reliable when eigenvectors are orthogonal, and that's for matrices that are symmetric or anti-symmetric, or there's a little bit larger class of matrices that includes orthogonal matrices. But beyond that, actually there's been a lot of discussion over many years of eigenvalues. And for problems that are not controlled by symmetric or anti-symmetric matrices. And the alternative, the more refined idea of pseudo eigenvalues is now appearing in important book by Trefethen and Embry, and with many examples. Okay, I won't pursue that. Right. So this is some basic facts about those matrices, all of which are one-dimensional. Now, this board prepares the way to get into 2D and 3D. So I just want to ask, what does and we didn't really do the heat equation or the wave equation in 2D, but we could have. The von Neumann test would be straightforward, but now I want to think about the matrices. What does the two-dimensional second difference matrix look like? Okay. What I'm going to do, just to look ahead, I'm going to use MATLAB's operation called cron, short for Kronecker, to create a 2D matrix out of this 1D center difference matrix. So if I think now about center differences, second differences, so I'm approximating uxx plus uyy, or really I'm approximating minus uxx minus uyy, because that k approximates minus the second difference. What do my matrices look like? What's their bandwidth? How expensive is it to invert them? These are the key questions. What's the matrix K2D that corresponds to, gives me second differences in the x direction plus second differences in the y direction? Okay, so I'll write K2D for that matrix. All right, let's get some picture of it. First of all, so I'm imagining, let me imagine that I'm on a square with a square grid, delta x in both directions. Yeah. Square grid, let me say n mesh points each way. So n, I don't know whether I'm counting, right now I won't worry, whether I'm counting the boundary ones or not, probably not. So n, I'll say n points, so n delta x, and in this direction, n delta x. So my matrix is of order, it's of size n squared. The number of unknowns. Now I will be a little more careful. Here, let me take the boundary values as given. They're not unknowns. So n in this picture is 4. 1, 2, 3, 4 unknowns there on a typical row. And now I have to give them a new number. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. N being 4, n squared is 16 for that particular square. Okay. So my matrix is 16 by 16. But somehow I want to be able to create it out of 4 by 4 matrices like K. So K1D, which I'm just going to call K, is, well, Kn will be the 4 by 4 one, 2 minus 1. So that's the matrix that gives me second differences along a typical row or down a typical column. But now what am I looking for? I'm looking to do both. Second differences in a row and a column. So if I pick a typical mesh point like number 11, mesh point 11, let me blow up this picture here. It's going to be influenced, mesh point 11, by 10 and 12, the second differences in the x direction, and by 7 and 15, notice those are not so close to 10 or 11, the second differences in the y direction. So let me blow that up. So here's mesh point number 11, corresponding to row 11 of K2D. So what is, so I guess I'm asking what row 11 of K2D will look like. Okay, so here's mesh points 9, 10, and 12. So I have a second difference in the x direction from uxx. From minus uxx, that means I can put a minus 1 there, a 2 there, and a minus 1 there. And now I have the same in the y direction with 15 and 7. So I have a minus 1 in column 15, a minus 1 in column 7. So I have a 4 minus 1s, and then another 2 more for the center gives me a 4. So a typical row will have, it'll be sparse, of course. It'll have a minus 1 in position 7, a minus 1 in position 10, a 4, a minus 1, and a minus 1 over there in position 15. That's a typical row of K2D. It adds to 0. If Gershgorin got his hands on this matrix, he would say that since all the rows, the 4 will be on, will the 4 be on the diagonal? Yes. The 4 will be on the diagonal all the way. Yeah, I guess let's see a little bit more clearly what the matrix K2D looks like. Yeah, this is probably the most studied matrix in numerical analysis because it's a model of what stays nice and what gets more difficult as you move into 2 dimensions. So some things certainly stay nice. Symmetries, so properties of K2D. K2D will be, it'll be symmetric again. It'll be positive definite again. And so what does K2D contain? It's 16 by 16. And a typical row looks like that. That's a typical interior row. What does, maybe, if I took the first row, what would the very first row look like? If I put row 1 above it. Let me draw row 1. So what's the difference with row 1? These are boundary values. These are going to show up on the right-hand side of the equation. They're known numbers. They don't involve unknown things. So the only neighbors are 2 and 5. So I'll still have the second difference, -1, 2, -1, and -1, 2, -1. Still this 5-point molecule with 4 at the center. But there won't be so many neighbors. There'll be the neighbor at just to the right, neighbor number 2, and there'll be neighbor number 5 a little further along, and that's it. It's like the 2 minus 1 boundary row. It's a boundary row. And a boundary row hasn't got as many -1s because it hasn't got as many neighboring unknowns. That boundary row would have 3 neighbors. Row 2 would have a 4, -1s, -1, but nobody there. So now I'm going to try to draw K2D. Or let me try to draw K2D. Yeah, I can do it. K2D will have from the UXX, the second differences along the rows, I'll have a row 1, it'll have another K on row 2, it'll have K on a K for each row. These are blocks now. That's of size n by n. So all of those are, so the whole thing is n squared by n squared. Actually, I'll stop here. If I wanted to create that matrix with the same K on, somehow the identity is in there and the matrix K is in there, and that's, let's see, it's one or the other of those. I guess it's the first one. So what's this Kronecker product? Now I'm saying what this construction is that's very valuable because it allows you to create matrices. And if you created K as a sparse matrix and I as a sparse matrix, then the Kronecker product would be automatically dealt with as a sparse matrix. Okay, so what's the rule for a Kronecker product? You take the first matrix, which is the identity, and the rest zeros. So that's I. And then, so that's 1D. And then you multiply, each entry in I becomes a block with entry Aij times this guy K. Well, this will be the 0 block, this will be the K block, this will be the K block. I take those 1s and multiply, and those 0s and multiply K, and that's what I get. So you see it's now, the Kronecker product is a bigger guy. If matrix A was P by P, and matrix B was Q by Q, then the Kronecker product would be P times Q by P times Q. It would be square again. It would be symmetric if A and B are symmetric. Actually, it would have various nice properties. Its eigenvalues would be the products of the eigenvalues of A times the eigenvalues of B. It's a very handy construction. And here we saw it in a pretty easy case where A was only the identity. Well, let me do this case. What does the Kronecker rule produce here? Okay, so I take this first matrix and I put it in here. 2, -1, -1, 2, -1, -1, 2. Okay. So that's the matrix K. And now each of those numbers multiplies the second thing, which here is I, so it's 2I, minus I, minus I, 2I, minus I, minus I, minus I, minus I, 2I, and 2I. Now that is the second difference matrix that does all the columns. And when I add those, so now I'm going to add that to that. They're both size n squared. They give me K2D. So the neat construction of K2D is cron of IK plus cron of KI. That's the matrix, and let's look at what it actually looks like. We're seeing it block-wise here. We saw it row-wise here. And maybe now we can take one more look at it, assemble it. So K2D, whoops, wants to disappear. So I plan to add that matrix to that matrix to get K2D. Okay, so it will have, since they both have 2's on the diagonal, it'll have 4's on the diagonal. So 4's all the way, but it'll be block-wise. So what's a typical, up here, this block is K plus 2I. So that block goes down to a 4. Sorry, yeah, 4. Now the K contributed minus 1's next to the diagonal. And I guess that's it, right? K plus 2I has that block as, that's the 1, 1 block. And why is it? So we're seeing, have I got it right? Yes, so we're seeing the neighbors to the right and left, but now let me bring in, only now come the neighbor above or below. And that comes from this off-diagonal block minus I, which is then a minus 1's to minus 1's. Okay. And these are all 0 blocks. And here will be a minus the identity block. Then another block, the diagonal blocks are all the same. And another minus the identity. Now we're getting to interior mesh points where we see typical rows. So a typical row has the 4's on the diagonal, the minus 1's left and right, and the minus 1's far left and far right. And of course, what I'm going to ask you is, what's the bandwidth? Here we come to the key point now. What's the bandwidth of this matrix? I only have 2 non-zeros above the diagonal on a typical row, but I have to wait n diagonals before I get to the second one. So the bandwidth is n, because I have to wait that long. And then the operation count, if I just do ordinary elimination on this matrix, the operation will be the size of the matrix times the bandwidth squared. We can easily check that that's the right count of operations for a banded matrix. This is operations on a banded matrix. Okay, so what do we get? The size of the matrix is n squared. The bandwidth is n. And it gets squared, so we get n to the 4th. Okay. It's getting up there. If n is 1,000, we've got a serious size matrix there. Still a very sparse matrix, so it's not like give up. But the question is, does the matrix stay sparse as we do elimination? And that's the center of the next lecture. What can we organize elimination? How closely can we organize elimination to preserve all these zillions of zeros that are in between here? They're easy to preserve down here, way up there, but in this intermediate, those diagonals tend to fill in. And that's not a happy experience. And it's even less happy in 3D. So let me just do this same calculation for 3D, and then we're done for today. So K3D, you might like to think how K3D could be created by the cron operation. Let me just imagine it. So what's K3D looking like? I've got 3 directions, so I have a 6 in the center and 6 minus 1s beside it. And so 6 goes on the diagonal of K3D. 6 minus 1s go in a typical row, and how long do I have to wait till I reach the last one? So I'm again going to do the size, which is the matrix size is going to be like n cubed. And what's the bandwidth going to be like? Maybe I ask you now. What do you think for the bandwidth? How long, if I just number it in the simplest way, and that'll be the key next time, is there a better numbering? But if I just number along rows until the rows fill up a plane of rows, and then I move up to the next, in the z direction, to the plane above, then I have to wait. Yeah, this was the x and y. So this gave me a bandwidth of n, but that's not the bandwidth because I have to wait until I've finished the whole plane until I go up to the next plane and catch this chap. So the bandwidth is n squared. And then the operations, which are size times bandwidth squared, we're up to n7th. And that is a really horrifying exponent to see, n to the 7th. That means that even for a moderate a problem in 3D with a moderate number, say 1,000 unknowns in each direction, we have we're looking in theory at a cost that we can't afford. Of course, there's a lot to do here. So there's a lot to do if I stay with direct methods, and that's what I'll do for the next couple of lectures. And then it's really in 3D that iterative methods become essential. I mean, this one I could do those by direct methods, 2D, by a smarter direct method than any I've tried here. But in 3D, even smarter elimination is facing a serious exponent and loses to iterative methods. So that's what's coming. Actually, so today's lecture, you see with the simplest possible matrices what the central questions are. Okay, thanks. And I've got homeworks coming back from Mr. Cho, and I'll collect any that are ready to come in. Okay, and see you Wednesday.